For the introduction, energy comes in the form of pressure, velocity, and height of fluid without energy exchange due to the viscous dissipation, heat transfer, or shaft work. The relationship between these three forms of energy was stated by Daniel Bernoulli from 1700 years to 1782 based on the principle of energy conservation. Bernoulli's theorem related to flow that based of the assumption which are steady flow, incompressible fluid, and no loss of fluid friction. The validity of the Bernoulli equation will be studied in this experiment. Bernoulli's principle associates fluid pressure with height and speed. The Bernoulli equation can be used to calculate this parameter in water, air, or liquid with very low viscosity. It has many applications in the engineering fluid dynamics, from aerospace wing design to plumbing for hydroelectric plant. For example, in the case of a hydroelectric plant that use water from a mountain reservoir, knowing the elevation change from a mountain reservoir to a plant in the town helps engineers determine how fast water will flow through the power generating turbine at the plant. According to Miller R.W., energy conservation laws are a key determinant behind the decline of Bernoulli's principle. Bernoulli's principle stated that in a fluid that flows stable, the sum of all mechanical energy, including kinetic energy, dynamic head, fluid pressure, and potential energy, must remain the same at flow points. Therefore, if one type of energy increases as if kinetic energy increases, then another type of energy such as potential energy, the pressure decreases to make the final amount the same as before. According to Bernoulli's equation, a flowing fluid has three things which are head, pressure, kinetic energy, and potential energy. The content of Bernoulli's principle states that when the compressed fluid flow is stable in the channel, with increasing flow velocity, the static pressure of the fluid will decreases. In other words, fluid static pressure increases with decreasing flow velocity. However, the magnitude of the static pressure and the kinetic pressure is constant. From Bernoulli's principle, it can be said that density and pressure are inversely proportional to each other, means that high density fluid will give more pressure than low density fluid. In horizontal pipes, where the inlet and outlet are at the same height, the quantity Z can be extracted to give a new equation to the Bernoulli principle, which we can calculate the height at each flow point. During this experiment, only water passed through the tube. Based on mass conservation, the amount of liquid rate is constant. Objective for this experiment is to study the effect of area of the flow velocity and fluid pressure by using the tensiometer, to compare the behavior of ideal and real fluid by using the Bernoulli's equation, to observe the fluid elevation through the tube with the different flow rates, to determine if the variation in static pressure head along the length of the tube that can be predicted by using Bernoulli's equation, to investigate the flow of water in a tapering horizontal tube, and lastly to determine if the total pressure head remains constant along the length of the tube as the Bernoulli's equation predicted.
Okay, now let's move to experimental section where I will show you how it will look like. Okay, let's go. Okay, here is what you need in this experiment based on what you have at home. First, what you need is clear water, follow with food coloring so that you can see the water flow clearly. Then two clear pipes that have different diameters, which are 8mm and 10mm. And lastly, two different sizes of the plastic bottle. Drop a few drops of food coloring in water, and then by using a screwdriver, make a hole at the plastic bottle so that clear pipes can fit into it. Just like this, but make sure to remove the plastic tag first so that you can see the water flow clearly. By using masking tape, put it around the pipes to prevent leaking. Cut the clear pipes to 20, 25 and 30 cm. Put the pipes in the small bottle, then open the lid of the bottle so that you can see the water flow through it. Take the time of the water flow until the water stops flowing. By using the same water, repeat the steps for the next diameters and lengths, and then you can record the data.
I will explain about the data from this experiment. This tabulated data shows the different diameter and length of pipe that we used in this experiment. We can see that time taken for water to flow from higher bottle to the lower bottle using large diameter, which is 10 mm, is less compared to the small diameter pipes. The shortest length of pipes take less time to water to flow compared to the longest length of pipe. From the first data, the velocity and flow rate of water can be calculated. The velocity of water is calculated by using the formula length of pipe divided by the time taken, and the flow rate of water is calculated by using the formula volume of water in the bottle divided by the time taken. As we can see, the small diameter and the shortest length of pipes that we use give small values of velocity and the flow rate. So, I illustrate our experiment with this figure. As you can see, it consists of 3 points, point A, point B, and point X. And also the height of water level of bottle A, ZA, and height of water level of bottle B, ZB. H is the max height of pipes that connecting between bottle A and bottle B. By applying the Bernoulli equation, we can find the velocity of water and the pressure at X. So this is the equation to find the velocity. As we know, in this Bernoulli equation, we cancel out PA and PB because it is the same value, which is pressure ATM. And then the equation left is only half rho V square equal to rho G delta Z. In this equation, we cancel out the density on the both sides, and then the equation left for V equal to square root of 2G delta Z. We substitute the value of delta Z, which is ZA minus ZB, and then the value of G, and then we get the V equal to 9.9 cm per second. To find the pressure at X, we rearrange this Bernoulli equation, and we get Px equal to pressure at A minus rho GH plus rho G ZA minus half rho VA square, where we substitute half rho VA square equal to rho G delta Z. And then the final equation we get is pressure at X equal to pressure at A minus rho GH minus ZB. And we substitute pressure at A, as we know PATM equal to 101.3 kPa and H equal to 10 cm, and then we get the final answer.
Discussion for siphon experiment. Bernoulli's principles state that an increase in the speed of a fluid occurs simultaneously with a decrease in static pressure or a decrease in fluid's potential energy. Bernoulli's can be applied for different types of flow, resulting in various forms of Bernoulli's equation for different flows. Bernoulli's principle can be derived from principles of conservation of energy, which is static pressure plus dynamic pressure equal to total pressure. Practical siphon works because gravity pulling down the taller column of liquid. It leaves reduced pressure at the top of siphon. This reduced pressure means gravity pulling down on shorter column is not sufficient to keep stationary liquid against atmospheric pressure. At this moment, atmospheric pressure pushing it out into reduced pressure zone at top, so liquid will flow from higher pressure area to lower pressure area. These are the results for diameter tube of 10 mm. As we can see, the longer the length of tube, the more time needed to fill up the bottle. While these are the results for diameter tube with 8 mm. It shows the same as diameter tube of 10 mm. The longer the length of tube, the more time needed to fill up the small bottle. The table shows the overall result for both diameter tube. Based on the experiment, we can see that the narrower the diameter of tube which increase the pressure, the more time needed for the bottle to fill up. We can conclude that the time needed for bottle to fill up affected by the length of the tube. The equation that we have to take to prevent any mistake. Make sure the height of liquid in first tank are the same for every reading to make sure the same atmospheric pressure will be applied. Second, start the timer from the moment the cap of bottle were opened.
For the conclusion, in this experiment, aim objective was to discuss the behavior of ideal and real fluid, and on the basis of the test result, it can be conducted that the experiment was successful. This is because of the friction losses in the real fluid, as ideal fluid does not have friction losses. Besides, the validity of the Bernoulli equation when it is applied to a steady flow of a water through a tapered duct is occurred. As shown in the graph, that decrease in area of flow decrease the height of water means they are directly proportional to each other. From the experiment, we can conclude that when there are decreases in area of flow, thus there is an increase in velocity and decreases in the flow pressure of the fluid. This type of information is very useful in the case if nozzles, jet, and diffusers. With that, we thank you.